In this video, we're going to look at a polyatomic cation, and then we're going to show how things like polyatomic cations or other things with polar covalent bonds where we have an acidic hydrogen present as a result of the polar covalent bond undergo acid reactions to lose a hydrogen atom. So, getting into it. So I want to look at a polyatomic cation in this case. And a good one to start with is ammonium. So ammonium has the formula NH4, and then we're going to add a positive charge. Okay, so what this means is that we're going to take our elements which include a nitrogen with 5 dots around it, a hydrogen, and then 4 hydrogens with 1 dot around them. And we're going to remove an electron because that will give us an overall positive charge. So we need to remove an electron from any one of these species. Now, what I might like to do is remove an electron from a hydrogen atom because that is kind of more chemically correct. That would give us one H plus or a proton. Remember, a hydrogen cation by itself is a proton. But maybe another way to do it that's a little bit easier to see, especially in the early going, is to remove one electron from the nitrogen atom. So I'm going to put an X over the electron around the nitrogen atom. That's going to give me a nitrogen with 4 dots. So we now have a nitrogen with 4 dots. Okay, now that's helpful to see because if we add that to 4 H dots, hopefully you can kind of see how this Lewis dot structure could come together. We could have a hydrogen adding to the east, north, west, and south to give us NH4, which would then have, instead of a Lewis dot structure, a Kekulé structure like this. Note it doesn't have any lone pairs anymore. One of the lone pair electrons was lost to us for us to have a positive charge. It's up here, our lost electron. So now what we have to recognize is if we're going to lose an electron, we have to have now an overall positive charge of +1, right? Because we didn't lose any protons. All of our elements and their corresponding protons went along for the ride, but one electron was lost from the overall molecule. Again, it could have been from one of the H's or a nitrogen. I could have picked, as long as I connect everything appropriately, I get the exact same outcome. Okay, what that means then is we're going to have an element with a formal charge of +1. So, where is the formal charge of +1? Well, there it would be. In this case, if we look, the H's are all the same. The H's all have 1 bond. I'll just show it as kind of like hanging off into nowhere with a squiggle. That's fairly actually kind of common notation or nomenclature. Okay, anyway, so its formal charge we're going to have being equal to its group number, its number of bonds, and number of electrons that are not in bonds. Okay, so for hydrogen, that's going to be equal to group number 1 minus 1 bond minus 0 electrons equals 0. All of the hydrogens are neutral. So then, by process of elimination, the nitrogen must then have a +1 formal charge, but let's figure that out. So the formal charge of nitrogen, in this case, we have N with 4 bonds and no lone pairs. So that's a group 5 element. It has 4 bonds. It has 0 non-bonding electrons. It's going to give us a +1 charge. So that +1 corresponds to the formal charge that I've shown over the nitrogen atom. And because it's the only formal charge in the molecule, we now have a polyatomic cation with an overall charge of +1. Now, I mentioned one way to, another way to do this is to take nitrogen and leave it alone, and instead focus on the 4 hydrogens, and let's cross 1 electron out. What that gives us is that gives us nitrogen with 3 H dots. And if we connect those 3 H dots to the corresponding spots that have 1 electron on the nitrogen atom, we would get a Lewis dot structure like this. Okay, so it turns out that this molecule is overall neutral. This is a molecule called ammonia. So ammonia, as opposed to ammonium, is kind of the nitrogen analog of water, NH3 in this case. And it's neutral. If you look, the hydrogens all have 1 bond. Now, what about the nitrogen in this case? Well, its formal charge is also equal to 0. The overall thing is neutral, but that's not all that we have. In addition to the 3 hydrogens that we were able to load onto the nitrogen by having 1 electron combined with another electron, we also have an H where the electron was crossed out. That's equivalent to us showing H+, which again, I keep calling a proton. Why? Because it's a single subatomic particle. If you take the hydrogen atom and remove 1 electron. Now, what can the proton do? Well, the proton, a single subatomic particle, is so desperate for electrons, is so desperate to fill its version of the octet, which is just 2 electrons, that it will actually find a way to sort of meet up with the NH3 to form something like this. So the H is going to actually just jump onto a lone pair of electrons. So it attaches to a lone pair and makes a bond. There, we just did chemistry. Chemistry is really just making and breaking bonds, covalent bonds usually, these things with these attachments of 2 nuclei that are just done by 2 electrons. So we have 1 subatomic particle, the proton, that's so desperate for electrons, it's just going to jump onto the lone pair of electrons and the nitrogen. The nitrogen does seem to get the raw end of the deal. The hydrogen now has an octet. It's now forming a bond with nitrogen. So the bond forms. And we get something that looks like this. Okay, I basically am now showing that the 2 electrons that were once a lone pair are no longer a lone pair and instead are now a covalent bond. This can happen from an orbital perspective. We would just have the 1s orbital of that hydrogen atom, which is now empty, just overlap with the orbital housing that lone pair of electrons. We've seen this molecule before. NH4 has a +1 formal charge. So the charge moved from the hydrogen to the nitrogen. Charge moved from H and to N. This is an example of an acid reaction. And really, it's a version, if you've seen this before, I'm just covering my bases. It's a Bronsted acid reaction. Anyway, for us, for now, an acid reaction is H+ adding to a lone pair. So the H plus adds to the lone pair. One really good exercise to do at this point is to just show the formal charge of H plus. So the formal charge of H plus is, well, it's H not bonded to anything. It's group 1. If you notice, I keep writing group and number of bonds and number of unshared electrons or non-bonding electrons. I keep writing that because it's so important. Okay, anyway, we have to know the formula. 1 minus 0, that's plus 1. That's just good to do at least once in our career. So that's H plus. One thing that I want us to start appreciating in this last lecture of Learning Module 1 is that acid reactions are reversible. Acid reactions are reversible. Let's just take a generic element with a lone pair of electrons. So we have my lone pair of electrons. I'm going to take a generic element and I'm going to label it as A. A can react with H plus to form I'm just showing kind of an intermediate complex, if you will, to form a bond to H. Okay? Now, this is our acid reaction that we just saw. A lone pair and its 2 electrons become a bond. Again, this is chemistry. The formation of bonds between 2 elements that were once not bonded to each other. So we have a lone pair, it engages H plus, become a bond. What we like to do in this case is to just kind of make the charges a little bit easier. We're going to say that A originally was an anion. Maybe it was a polyatomic anion, maybe it was just a single element anion. We'll look at an example here in a second. But A minus will engage H plus to make now a neutral molecule. What we saw in the case of NH3 reacting with H plus is that the nitrogen charge went from 0 to +1. Anytime something reacts, I get to use that word now, it's kind of fun, reacts with H plus, its overall charge and its charge on the formal charge in the atom both increase by 1. So charge increases by 1. That is to say, we went from -1 to 0 in this case. And in the case of NH3, we went to NH4 plus, or 0 to +1, when we added an H plus. Okay, so let's look at a real example. Let's say we have Cl minus. Now, how would chlorine have a negative charge? Well, we can figure that out. Cl minus, its formal charge is equal to -1. Okay, I mean, I know it's the entire molecule. That's not a correct term for us, but it's a single element. Anytime you're looking at a single element, you can use this formula to determine its charge. If it's within an entire molecule, we say it's its formal charge. Okay, so the formal charge of chlorine in this case is -1. That's equal to the group number, which is 7, minus the number of bonds, minus the number of electrons. Okay, what I'm saying here is I want to look at chlorine reacting with H plus to form, in this case, ClH. this has, I'm just going to zoom this out a second. This has parallelism, where we have ClH is the same as AH in our previous case. We have ClH now being neutral. Now what I'm getting at with this point down here is, what is the arrangement of the chlorine atom? How many bonds does it have? How many lone pairs does it have to have a -1 formal charge? Well, it's chlorine by itself, so we have 0 bonds. So what we really need to solve is the number of unshared electrons it has. So if we solve for -1 equals 7 minus 0 minus x, then x is equal to 8. Okay, so we have 8 unshared electrons around our chlorine atom. That comes from 4 lone pairs of electrons. Anytime you have a halogen atom, whether it's fluorine, chlorine, bromine, or iodine, if the halogen atom sits as a negatively charged element by itself, it's going to have 4 lone pairs of electrons. You could also think about it as being negatively charged, where we're just going to dump 1 electron into the valence shell. The valence shell originally had 7 electrons. There's many ways you could think about it. This is just kind of one. Okay, so we had the negative charge, negative formal charge of -1. We then figured out it must have 4 lone pairs of electrons. Again, a few ways that you could do that. So what that means is that the Cl is going to have 3 lone pairs of electrons after it reacts with the hydrogen atom. We could even check our formal charge calculation. 7 minus 1 minus 6 is equal to 0. It's now neutral. Why am I showing you this? Well, again, I wanted to demonstrate an example where we have kind of, we can see how these two pieces of information are the same. It's just a real example where we've actually defined A. Now, A could be something much more complicated, like a polyatomic anion. It could even be carbonate, like we looked at in the previous lecture, although we'd have to add 2 H's to the molecule. In all the cases, though, the H's bind to or form a bond with electrons that were once part of a lone pair. The other reason why I wanted to show you this was I wanted us to recognize that ClH, this is equal to HCl, which is hydrochloric acid. Now, this term acid here is important because this just describes a very useful property. In the case of acetic acid, it wasn't so useful because acetic acid is a weak acid. Hydrochloric acid is a strong acid, though. Acids are a group of molecules. Acids readily donate acidic hydrogens, we've looked at that before, as H+. That is to say that we could take our acid and it will undergo a reaction to give rise to H+, and because we must balance the number of elements on either side of a chemical reaction, we form something else. Well, generically, what we do is we have HA doing this reaction to form H+, and then this is where that A comes in. That's why we use the variable A as opposed to X here, is because we often use A to describe acids. Now, in this case, we're forming H+ because we defined HA to be an acid. Now, what is left behind? Well, we have A, but if you look at this, this is the reverse of what we saw on our previous page of notes. There's a way to have a light color here. That is to say, the thing that we wrote down on the previous page was this reaction flipped around where we had A reacting with H+ to give us HA. So if we're going one way, basically what I'm saying is whatever happens in one direction must happen in the other direction. This is what we call a reversible reaction. Said another way, and more succinctly, for this reaction to work, as we see in our previous page of notes, A must have a negative formal charge and have a lone pair of electrons. The lone pair is a place for the hydrogen to jump onto to form HA in the reverse reaction. Now, alternatively, another way to think about it is the electrons that were once part of our covalent bond, and covalent bonds always have 2 electrons, those 2 electrons now become the lone pair of electrons. Thinking about not only what's happening to the elements, but also the subatomic particles. So HCl is notorious for this. If you mix HCl with anything, I mean, if you get it out of its gas state and into water, for example, it will do this reaction where it donates an H+, and it actually puts the H+ on a bunch of water molecules. The lone pair on the oxygen of the water molecules accepts that H+, and what we're left with is Cl-, because the 2 electrons that were once bound to the hydrogen atom are no longer shared with hydrogen, and they're now on chlorine by itself along with the other 3 lone pairs of electrons, giving it 8 lone pairs of electrons total for a net formal charge of -1. Now, what I want us to be able to do is, can you draw the conjugate acid base pair? Okay, some new terms here, but it all utilizes what we've talked about above. Here is our generic acid. It's reacting like an acid. In that it's giving H+, and just to balance the equation, we have to leave behind A- with a lone pair of electrons. Now, some key terms here that I alluded to are we've got HA and we've got A-. So A- is called the conjugate base. And HA is called, so A- is the conjugate base. HA is a generic acid, yes, but in this equation, it is the conjugate acid. So the conjugate acid is the structure, let's get the green in there, structure that resulting from adding an H+, or before H+ loss. The conjugate base is the structure resulting from loss of H+. A little fast there. Structure resulting from loss of H+. So if you look, we have HA, that loses an H+ to give A-. The H+ is the thing that reacts with everything else, but it's A- that we define as the conjugate base. And understanding a conjugate acid and a conjugate base is super, super important for understanding acid-base reactions. And acid-base reactions are just like probably the most important reaction that we can study on paper anyway. Okay, let's look at some examples. So let's say we have HCl reacting to form H+ plus Cl-. We have OH- plus H+ reacting to form HOH. Say we've got this molecule reacting to give H++ this molecule, and then let's say we've got ammonium reacting to give this molecule plus H plus. What I want to do is for each of these, I want to label the conjugate acid, which I'll call Ca, and conjugate base, which is Cb above. So we got Ca and Cb that we need to label. So the thing that results from accepting an acid is the conjugate acid. So the Ca in this case is HCl. It's the structure that results after we accept H plus. And in these first three cases, it's the neutral structure. I'm going to stall a second before we get to the last one here. So in the first three cases, it was the neutral structure. For this last case, it is the positive structure. Why? Because that positive structure loses an H plus, to give rise to a new structure, which is NH3, and that's going to be its Cb. So kind of labeling the Cb now in every case. This is the structure that results from loss of H plus, or the structure that would like to pick up H plus. Okay, so a lot of stuff in this lecture, a lot of really important stuff, not only looking at polyatomic cations and expanding our understanding of formal charge, but also looking at what happens when H plus is kind of moved around between molecules and how we define things like conjugate acid and conjugate base. These are really important terms for understanding chemistry, much more broadly beyond organic chemistry, but it's important for understanding biology and bigger other fields in chemistry. One thing that I didn't touch on that it would be really productive if we knew how to do is to look at molecules and be able to predict what the structure would be after loss of the acidic hydrogen. Imagine this. I give you a problem. I say, identify the acidic hydrogen, then draw the resulting conjugate base. So you'd have to circle that acidic hydrogen, then draw the structure after you lose that conjugate base. I mean, let's just do one example so you can see what I mean. Okay, so we have our screen back in front of us. Sorry, I just think this is important enough. Predict the Cb or Ca, really. Okay, so let's say that we've got, and let's get into bond line structure mode here. Okay, so circle the acidic H atom. That's going to be, it's not very clear. Let's get a different color here. This structure, I'm going to draw a reaction where I lose that acidic hydrogen. So the bond that connected the nitrogen to the hydrogen is now severed, and instead we leave behind a lone pair of electrons. As that H plus walks away without any electrons of its own, it now has a positive formal charge. The nitrogen, in this case, let's think for a second, has a formal charge equal to 5, that's its group number, minus 2, oh, it had a lone pair up here, minus 2, I forgot about that, excuse me, minus 4. I forgot about that second lone pair for a moment. I was like, what's going on? Okay, so lone pair sticks behind. So we have a new lone pair of electrons, so 5 minus 2 minus 4, that's equal to -1. We put the -1 up here, and we have predicted the structure of the conjugate base. So this is our Cb, and this is our Ca. Okay, now I will really be done. Okay, so again, this is our first pass into chemistry, seeing and predicting what happens when bonds are broken and atoms start to move. Really important stuff. Okay.